In this video, we're going to learn about some more reaction types. In the previous video to this one, we learned about two classes of reactions called acid-base reactions. Acid-base reactions are just proton exchange reactions, where one species, which is called an acid, donates a proton to another species, which is called a base. And the other class of reactions we learned about in that video were precipitation reactions. And that's where you have two substances that are dissolved in water, so two aqueous solutions. You mix them together and they produce a product that doesn't dissolve in water. So this solid that comes out of the solution is called a precipitate, and that's why those are called precipitation reactions. In this video, we're going to learn about three kinds of reactions that all are under the kind of general category of what are called redox reactions. And redox is short for something, as you're going to come to find out in a bit. Oxidation was originally thought of just when something reacts with oxygen. That's where the name comes from, oxidation. So here's an example. If you leave titanium in the presence of oxygen for a long enough time, it becomes titanium 4 oxide. So there's a reaction of titanium with oxygen. That's considered an oxidation. Here's another example. This happens all the time on cars in northern Wisconsin. In the wintertime, if you react iron with oxygen, you get iron 3 oxide, which is what we commonly call rust, or it's one of the compounds that we call rust. So here again, you have oxygen reacting with something to produce an oxide of that compound. Now, these two are metals. You can also do this with nonmetals, but that was what originally people thought oxidations were. But then later on, chemists started to realize that you could have oxidation occur without oxygen, because they realized that what was really happening to these metals was they were losing electrons and becoming positively charged. So the titanium would lose 4 electrons and the iron would lose 3 electrons, and in the process, they would become positively charged. So what they started to realize is that instead of thinking about oxidation as the reaction of something with oxygen, they could make a broader category of oxidation reactions by just realizing that what really happens in oxidation is that you're losing electrons. Now, electrons are matter, and matter can't be created or destroyed in ordinary chemical change, which is what redox is. So something else must gain electrons if an oxidation occurs. And what was gaining the electrons was the other species that was involved in the reaction. So when the titanium lost 4 electrons to become titanium 4 plus, oxygen was gaining 4 electrons to become the oxide ion, the O2 minus ion, that would bond with it. So that half of the reaction is called reduction. So when something is oxidized, it loses electrons. When something is reduced, it gains those electrons. And because oxidation and reduction can't occur without each other, they always happen in pairs. There's never an oxidation without a reduction. And also the number of electrons that are lost by the oxidation is always equal to the number of electrons that's gained by the reduction. Sometimes it doesn't seem that way at first when you start working with these reactions, but once the equation is balanced, you realize that it's possible for the electrons to all come out even, reduction and oxidation. So because reduction and oxidation always occur together, we call these reduction oxidation reactions, or for short, redox reactions. Now, it was pretty easy when we were oxidizing these metals to become metal ions to track what was losing and what was gaining electrons. That's not so easy when ions aren't formed, because it's not quite so explicit where the electrons are going. So we have this kind of a bookkeeping method called oxidation numbers that would work in a situation like this. So this is where hydrogen is oxidized. Even by the old definition, this is oxidation because you're reacting with oxygen. But you're not forming any ions. H2O is a molecule. It's not an ionic compound. So we need another way of keeping track of that. And that's what oxidation numbers are. They're a bookkeeping method to keep track of where the electrons are moving when charge isn't explicit in the reaction. So here are some rules for assigning oxidation number. One of them is the oxidation number of a pure element is 0. So sodium, oxidation number 0. Zinc, oxidation number 0. And even diatomic molecules of pure elements, oxidation number 0. So H2, oxidation number 0, and N2, oxidation number is also 0. The oxidation number of a monatomic ion is whatever its charge is. So a sodium 1 plus ion, the oxidation number is +1. Sulfur 2 minus ion, the oxidation number is -2. You may notice here that the sign on the charge comes after the number, and the sign on the oxidation number comes before the number in these cases. That's sort of convention, but as far as I'm concerned, it doesn't matter. You can uh, just write them either way that you want. But the oxidation number of a monatomic ion, whatever that monatomic ion is the same as its charge. Remember, mono is 1, so these are one-atomed ions like the sodium and the sulfur that we have here. There are some rules we have for specific elements when they're in compounds as far as assigning oxidation numbers. One of them is the oxidation number of fluorine when it's in a compound is always -1. So that would be fluoride ion or fluorine when it's part of a molecular compound. No matter what, if fluorine's not by itself, it's always -1 if it's in a compound. Another rule is the oxidation number of hydrogen when it's bonded with a non-metal is always +1. And this is how you're usually going to see hydrogen. So it's a pretty good rule of thumb. Hydrogen is always a +1. Now there's one exception to that, and that is when hydrogen is compounded with a metal, then it's always going to be a -1. But this is rare. You're not going to see this very often. You may never see this in this class. The oxidation number of oxygen is usually -2. Most of the time, it's -2. Two exceptions to this are something called peroxides. And in a peroxide, you have O2 2 minus, in which the oxidation number is a -1. And then there's another ion called a superoxide, which is an O2 1 minus, and the oxidation number for that is a 1/2, as it turns out. But those are pretty rare. You're not going to see those very often. Peroxide shows up in a few ionic compounds, but you won't see those probably in this class. If you do, it would be pretty unusual. Another rule of thumb is that oxidation numbers, when they're added all up, will equal the charge on the molecule or the ion. The charge on the molecule is 0, so that means when you add up all the oxidation numbers, they have to add up to 0. And if you have a polyatomic ion, if it has a 2 minus charge, then all of the oxidation numbers have to add up to 2 minus. Or if it's a 1 plus, let's say, then all of the oxidation numbers have to add up to a 1 plus. So this we can use to figure out the oxidation number of things that we don't have a rule of thumb for. So here's an example. If we compare the oxidation number of nitrogen in NO2 versus in N2O, we will see that they have different oxidation numbers. In NO2, we have oxygen here, and oxygen's oxidation number is going to be 2 minus always. 2 minus twice for 2 atoms is going to be 4 minus total. So because this is a neutral molecule, I have to have a +4 for my oxidation number on nitrogen. Now, if we compare that with N2O, here again, oxygen's -2. It's almost always -2. But because the charge on this molecule is 0, that means whatever the oxidation number is on the 2 nitrogens, that must add up with the -2 to come out to 0. So that means that my nitrogen is going to have a 1 plus oxidation number, because 2 1 pluses give you 2 plus, and that 2 plus adds with the -2 to give me the charge on the molecule, which is 0. Another example, comparing SO3 2 minus, the sulfite ion, with SO4 2 minus, the sulfate ion. Oxygen is going to be -2 oxidation number. Oxygen being -2 3 times, that gives me a -6 total. So whatever the sulfur's oxidation number is, it has to add with -6 to end up at -2, which makes it +4. Because +4 minus 6 gives me -2. Now, if I'm looking at sulfate, oxygen's -2, and 4 of them gives me a -8. So whatever sulfur's oxidation number is, it has to add to -8 to give me -2. So that means my sulfur in this case has to have an oxidation number of +6. So how we can use oxidation numbers to track what's going on in a reduction and oxidation reaction, or redox reaction, is the species that experiences an increase in oxidation number is oxidized. The species that experiences a decrease in oxidation number got reduced. So if you track across an arrow what's going on with oxidation number, you can figure out what's being oxidized and what's being reduced, even if no ions are ever formed. So let's take a look at what's going on here. On the left-hand side, you have hydrogen, which is a lone element, a pure element. That has an oxidation number of 0. Oxygen also has an oxidation number of 0 because it's a pure element. In compounds, oxygen is usually -2, and hydrogen is usually +1. And that fits with our rule of adding up the oxidation numbers. 2 negatives plus 2 positives adds up to neutral, which is what water is. Okay, so what got oxidized here? Well, hydrogen went from 0 up to +1, so that's the oxidation. And oxygen went from 0 down to -2, so the oxygen got reduced. There's another piece of terminology that I don't think I am mentioning anywhere else here that you might want to be familiar with. Something that oxidizes causes another thing to get reduced. So the hydrogen in this case, by being oxidized, is called a reducing agent for the oxygen. And oxygen, because it gets reduced, allows the hydrogen to oxidize by collecting those electrons that it needs to lose. So that's called an oxidizing agent. Here's another example. In this permanganate, MnO4 ion, the oxygen is going to have a -2, which it usually does. -2 4 times is -8. So the manganese has to have a +7 oxidation number because it has to add together with that -8 to give you a -1 because that's the charge on the ion. Iodine is a monatomic ion, so it's going to have the same oxidation number as its charge, which is a 1 minus. MnO2, oxygen's -2. -2 twice is -4. This is a neutral molecule, so the manganese has to balance that out to 0. So the manganese has a +4 oxidation number. And iodine, I2, that's an element, just pure element, uncombined. So that's a 0. Okay, so what happened here? The iodine went from -1 to 0. That's an increase in oxidation number, so that's the oxidation part. And the manganese went from +7 down to +4, so that's the reduction. So the permanganate is the oxidizing agent because it got reduced and allowed the iodine to oxidize. And the iodine got oxidized, which makes it the reducing agent because it allowed permanganate to reduce. Here's another example. Chlorine, oxidation number is 0 because it's a pure element. Oxygen here is -2. Hydrogen's usually +1. And +1 and -2 is -1 when you add them together, and that matches the charge on the ion, so that's good. Chloride here is a monatomic ion, so its oxidation number is the same as its charge, -1. In this chlorate ion, -2 for oxygen, 3 times is -6. So to get up to -1, the chlorine here must have a +5 oxidation number. So in this case, chlorine is both oxidized and reduced. The chlorine to Cl minus, chloride ion, that is a reduction because it went down from 0 to -1. But the chlorine to chlorate, that's an oxidation because it went from 0 up to +5 in oxidation number. Now we're going to learn a technique for balancing redox reactions. Balancing redox reactions is not always as easy as balancing kind of ordinary molecular equations or even ionic equations because you have to sometimes add some species in. So there's a method for doing this. There's actually 2 or 3 different kinds of methods, but I'm just only going to teach you the one that I have found always works, or almost always works. But it'll always work in AP Chemistry. So here's the first step. You take your reaction, which is often going to be presented to you as a net ionic reaction, and you separate the reaction into a redox pair. Separate the reduction out from the oxidation. Now, you can assign oxidation numbers if you want to, and let's just do that. Here's oxygen here, and this is called the dichromate ion. -2, 7 times is -14. So that means the CR2s, the two CRs, have to give us positive 12 so that they add up with negative 14 to give us 2 minus. So each one of them must be plus 6. All right, sulfur and oxygen here. Oxygen's negative 2. Twice would be negative 4, so the sulfur must be plus 4 because this is a neutral molecule. This is a monatomic ion, so that's just 3 plus. And then here, oxygen's negative 2. Hydrogen's going to be plus 1. Minus 2 4 times is minus 8. Plus 1 is minus 7. So to get up to negative 1, the sulfur must be plus 6 in this case. All right, so chromium is being reduced from dichromate where it's plus 6 down to chromium 3 plus where it's 3 plus. And the sulfur is being oxidized from 4 in SO2 to 6 in HSO41 minus. Okay, now lots of times, most of the time, you don't actually have to do that because I can't have like CR2O7 2 minus become HSO4 because there's no chromium in it. So the product here has to be my CR3 plus. And the same thing with SO2, it has to make HSO41 minus because if it made chromium, that would not make any sense because there's no sulfur in there and there's no chromium on the left hand side. Okay, so there I've separated my reaction into my redox pair. This top one happens to be the reduction, and this one happens to be the oxidation. But I can separate them often into redox pairs without even thinking about which one is reduction and which one is oxidation. So that's the first step. The next step is for each of the two half reactions that you just created, balance all the elements except for hydrogen and oxygen. So on the left-hand side here, we have 2 chromiums and 7 oxygens, but we're ignoring the oxygen. On the right-hand side, we have 1 chromium. So to balance chromium, I'm going to put a coefficient of 2 out here. On the other half reaction, I have oxygen and I have hydrogen, but I'm ignoring those. I'm just looking at sulfur only. I have 1 sulfur on the right. I have 1 sulfur on the left. This half reaction is already balanced. So everything but hydrogen and oxygen balance with coefficients like normal. Then the next step is for each half reaction, you're going to balance oxygen by adding enough waters to balance the oxygen. So in the top half reaction, I have 7 oxygen on the left, but I don't have any oxygen on the right. Every water has got an oxygen in it. So if I add 7 waters to the right, I have now balanced my oxygen. Next half reaction. I have 4 oxygens on the right. I have 2 oxygens on the left. I need 2 more oxygens on the left. So I'm going to add 2 waters, and those 2 waters will now balance my oxygen. Next step. You have now just added some hydrogen, so almost always that's going to mess up your hydrogen balance. So you balance hydrogen with H plus ions. So on the right-hand side, I have now 14 hydrogen atoms and none on the left on the top reaction, half reaction. So I'm going to add 14 H pluses to this side to make that balance. On the bottom, I have 4 hydrogens in my 2 waters on the left. I have only 1 hydrogen on the right, so I'm going to have to add 3 H plus ions to bring this into balance. Okay, so now we balanced everything except for oxygen and hydrogen. Then we balance the oxygen with water. Then we balance the hydrogen with H plus. So now everything is balanced except for charge. So what we're going to do now is we're going to balance charge by adding electrons to the appropriate side. Let's take a look at the total electron count here. On the right-hand side, I have 2 3 pluses. So the total charge here is 6 plus. It's not really electron count. I'm just looking at charge. On the left-hand side, I have 14 pluses in my 14H plus, and I have 2 minus from my 1 dichromate ion. So that's a 12 plus total. I have to bring these into balance. So that means I need the left-hand side to be 6 steps more negative. So I'm going to add 6 electrons. So you're always looking at how much more negative do I want to make one of the sides, because all you can balance this with is electrons. All right, so now I'm going to look at the next half reaction. This is all neutral on this side, zero charge. Over here, I have three pluses and a minus, so that is 2 plus. So that means I'm going to add 2 electrons to this side. Now notice how I'm adding electrons to the left-hand side on the bottom half reaction, which we decided was an oxidation, because oxidation is losing electrons. Reduction is gaining electrons, and the top half reaction was the reduction, and sure enough, we added 6 electrons. So that means something was gaining electrons. In fact, it's the chromium. So once we've done that, the next thing we have to do is make sure that the electrons that we lost in the oxidation are the same as the electrons that were gained in the reduction. Here, we gained 6 electrons, but we only lost 2. So that means this can't be how this really happens. So what we're going to do is we're going to take this half reaction on the bottom here, and we're going to triple it, because 3 times 2 electrons gives us 6 electrons. So now we have these half reactions such that the electrons gained and lost are the same. Then the last thing to do is to just add the 2 half reactions together. So we'll take these half reactions and add them up. The 6 electrons are going to cancel out from both sides, so we can just leave that out. Electrons are always going to cancel out because we've adjusted them. All right, so let's write down what we have here. 14H plus Cr2O7 2 minus plus 6 water plus 3 SO2. That's everything on the left-hand side. And now we got 2 Cr3 plus 7 water plus 3 HSO4 1 minus plus 9H plus. And remember, the electrons we've already canceled out. Okay, so you probably are already realizing that we have waters on both sides and we have hydrogen ions on both sides. So we'll have to deal with that. So we may as well do that now. If I take 9 hydrogens away here, then on the left-hand side, I have 14 minus 9 is 5 hydrogens. And I have 6 water on the left and 7 on the right. So I can take these 6 waters away, and this coefficient just becomes a 1. So there's my overall balanced equation. One thing I should note that I don't think I maybe explicitly called out is that all the coefficients in that bottom half reaction had to be tripled. When we turned this from 2 electrons into 6 electrons, we multiplied by 3. So we have to multiply the whole equation by 3. So our 3H pluses became 9. H pluses are 1 HSO4, 1 minus became a 3. The 1 SO2 became a 3, and the 2 waters became 6. So I'm just going to rewrite this in a kind of a cleaned up fashion. That 10H plus ended up being 5H plus. And then we had Cr2O7, 2 minus. And then we had 6 waters, but they canceled out. 3 SO2. And then on the right-hand side, we had 2 chromium 3 plus ions. We ended up having only 1 water because it canceled out with the 6 waters. And then we had 3 HSO4 1 minuses, and then we had 9 H plus. No, we didn't. Those 9 H plus weren't there. Okay, so there's our overall balanced equation. Now, you'll notice that there's some extra hydrogen ions floating around in here. So that means this reaction can only occur in an acidic environment, in a place where there are free protons floating around in the solution to make this reaction occur. Redox reactions don't always happen in an acidic environment, and so we need to deal with that as well. So here's how we deal with balancing a redox reaction in a basic environment. In other words, in an environment where there is a predominance of OH minus ions, that's what bases usually are, rather than extra H pluses. So the first step is you just follow all the same steps that if it was an acidic environment, all the things that we just did. So let's do that with this half reaction. Without identifying what's redox, what's reduction, what's oxidation, I know that MnO4 minus has to be producing MnO2 because I have to have manganese in both sides. And I know that I minus has to be producing I2. So remember my steps, I'm going to balance everything that isn't oxygen or hydrogen. The top half reaction, I have one Mn on both sides, that's fine. I'm ignoring oxygen. The bottom half reaction, I have two I's on the right, so I put a coefficient of 2 in front of iodide to balance that. Next, I have to balance oxygen with water. I have 4 oxygens on the left. On the right, I have 2 oxygens, so I'm going to need 2 more oxygens. So I'm going to use 2 waters to give me my 2 extra oxygens. Don't have to do anything with oxygen on the second half reaction. On the top half reaction, I now have hydrogen I got to balance, which I balance with H pluses. And I know I can't have H pluses, but I'm just going to ignore that for now. I have 4 hydrogens on the right in my 2 waters, so I'm going to put 4 H plus in here. Okay, now I got everything balanced except for charge isn't balanced. On the right-hand side, I have a charge of 0. On the left-hand side, I have 4 pluses and a minus, so that's 3 plus. So I'm going to have to add 3 electrons to balance the charge. On the second half reaction, I have 2 minuses on the left. It's neutral on the right, so I have to add 2 electrons to balance charge. Now I have to have electrons lost and gained to be the same. So I have to multiply my top half reaction by 2 and my bottom half reaction by 3. And when I do that, I'll have 6 electrons lost and 6 electrons gained. So now I'm adding these up. Hydrogen is going to be 8H. I'm going to have 2 MnO4s. I'm going to have 6 I minus. Then on the right-hand side, back to the top half reaction, I'm going to have 2 MnO2 because I'm multiplying by 2 plus 4 H2O plus, on the bottom now again, 3 I2. And there's my balanced equation. Now, because I can't have this in an environment where I need excess H pluses, this can't be how the reaction ends up being. So what I do to deal with that is I neutralize the H pluses by adding OH minus to both sides. So because I have to neutralize 8 H pluses, I'm going to add 8 OH minuses. It's not an equation unless I do it to both sides. So I'm going to add 8 OH minuses over here, sum the whole thing up. And so now the H plus and the OH minus, that's an acid-base neutralization actually that occurs. That's going to give me 8 waters. Plus I have my 2 MnO4 minus, my 6 I minus, making 2 MnO2 and 4 water, 3 I2, and the 8 OH minus that I had to add. Okay, so now I can tune this up a little bit. 4 waters I can cancel from each side. So this coefficient 8 becomes a 4. And there's my balanced equation. It's occurring in a basic environment. It does not require me to have H pluses around. Okay, let's do some balancing practice. This is your opportunity to practice. So just stop the video, follow the steps, balance this in an acidic environment, and I will give you the answer here. You can just check and see if you're doing it right. Okay, there is your answer. If you didn't get that, go back and try and find out what you might have done wrong. More practice. Balance this in a basic environment. Stop the video. Follow the steps for balancing in an acidic environment, and then adjust by reacting the excess H pluses with OH minus to give you water. Add that to both sides. And I'll give you the answer in a bit. There's your answer. Check and see if you got that correct. Okay, here are the categories of redox reactions that you see. One type is called a synthesis. In a synthesis reaction, synthesis means like made up. You're making one product from two reactants. So an example of this would be sodium plus chlorine making NaCl. Sodium gets oxidized to a 1 plus ion, chlorine gets reduced. You can always spot a synthesis because there's only one product. Another type is called a decomposition. This is just the opposite of a synthesis. Here you're taking one species, a compound, and you're breaking it up into two species, which could be two elements or could be an element in a compound. An example of this would be hydrogen peroxide, H2O2, decomposing into H2O and O2. This is another type of redox reaction. You can always spot a decomposition because there's only one reactant. And then the third type is called a single replacement, or sometimes it's called a single displacement. And it has this general pattern of AX plus Y equals AY plus X. So there's something about X and Y that is similar, like maybe they're both cations or maybe they're both anions, something like that. And they sort of switch places in the reaction. And that's why it's called a single replacement. Double replacement reactions are either acid-base neutralizations or the precipitation reactions that we saw in the previous video. And those are not redox reactions, but a single replacement is. So here's an example of that. Silver and chlorine are bonded. Gold and chlorine are bonded at first on the left-hand side. Zinc is by itself. And then the zinc replaces the gold. That's what's going on here. They're both metals. They're replacing each other. And on the right-hand side, you have zinc with chlorine. And then now the gold is by itself. That is a single replacement. So you can spot single replacements because typically what you're going to have is a compound plus an element makes a compound plus an element. So single replacement, synthesis, and decomposition reactions, all those three are examples of redox reactions that you see out in the real world.